Christian, can you hear me?
Yes, I can.
Okay, thanks. Camera, that looks good. And this one is almost good. It's kind of crucial question, so I'll let you actually cluster to pairs or 3 people or something, and wonder about this big concept, difference in the concept that is relevant for homework 2 and much more relevant in homework 3. And it's both use ray tracing, ray shooting, and by the way, some people discussed the idea of using texture or image wrapping or even image matching that are texture you'll have in later homeworks, homework 4 and so on. And image wrapping we don't need at all, and homography we don't need, at least not directly at all. It will be hidden underneath there, and maybe we'll talk about it. But, and definitely in homework 2 and 3, nothing that involve anything but pixels. That is the first thing that I'll do when I'll check your code is which library you are using. You do not need anything beside something that allows you to do one matrix 3 by 3, like not the whole image, 3 by 3, 4 by 4 with homogeneous coordinates. So multiply two matrices, multiply by a vector of 3 or 4 dimensions. And the other libraries that you can use are, of course, to read the image/images for billboards or to write them. But nothing more fancy. And the equivalent, of course, if you're using Python, which so please don't submit anything in homework 2 or 3 that do more fancy, that use any more fancy libraries. If you have any doubts, ask me. Okay, for homework 2 and 3, this little gap that I want to mention is that we need one loop that generates all the pixels, that is all the rays, and then we need a loop that runs through all the objects. We got all the objects in data in an array that basically the library that reads the JSON files. If you didn't say it, yes, JSON file, you're also most welcome to read from the file. No need to parse it yourself. But once you have the array, the database that contains the billboards with all the properties, in homework 3 it's also the sun and the type of light, and the spheres, you need two nested loops, right? One that runs for the pixels and one that runs on the objects. And the outer loop can be that I'll run through all the objects, and now for each object I'll go over all the rays, and if this ray hits this one object that I'm concentrated in, I'll do something. Alternatively, the outer loop would generate pixels and then generate rays, and the inner loop will take a ray R, presumably as a parameter, but here I'll take an object or as a parameter. Here I'll take a ray as a parameter, and if this ray hits this object, then I'll do something, of course. And I want to ask you, which one do you suggest to use in homework 2, which doesn't make a huge difference, and which one, but if you're, since homework 3, I could have skipped homework 2 and let you submit homework 3, but I thought that I'll split it because homework 2 doesn't have any shading and other things homework 3 does. And I broke it into two, but homework 3 completely includes homework 2. So anyhow, which one will you do, and please discuss it with your neighbors because you finally decide. Let's take 2 minutes. It's kind of.
I originally the top one.
No, because.
The thing like you have 600 or 600 rays in the top one. You're doing that for every single object.
Well, but at the same time, yeah.
Right.
Someone's like when you put all the pixels in it, you can generate all those. It's like
I guess you can.
That's true. But so if we go through each object and actually each race,
Well, there's this.
It depends
Wait,
on how
each time.
if you ever really want to adjust the amount of time
the objects to
Yeah, but like in general though, like why would you want to loop through every single ray for every single object?
And to interrupt your discussion, it's probably not a good idea to write it all as a one big two-nested loop, but probably you want to break it into function and do something with these function methods, whichever you want to call it.
yeah, I don't get that much time.
Do we have consensus?
At the bottom. I like bottom.
And people say this one, which is the correct answer, but why?
It's more if you have a ray for every pixel, right? In the top one, you're looping through that ray multiple times for every object, whereas in the bottom one, you're only looping through every individual ray once.
Computationally wise, I think that in homework 2, it is the same amount of work, actually. It's in big O values, it's a number of rays times the number of objects. And if I assume that for every billboard you take constant time, then it's m times n. So that's not where they are. That's not a huge issue. That's why I said in homework 2, I think that you can do either way. Not that in any way it's recommended to not use sub-functions, but yes.
For the top one, you to save the depth value, like the distance, and since you're going for each object, you have to save it for each pixel, because each time you iterate over a new object, you have to recheck the value. Versus the bottom one.
It's tempting to use the first one because the first one is simulating the buffer. But homework 3, which is, to remind you, homework 3, what you see in this, I'm just showing you, I'm just flexing, You see a camera. I couldn't avoid myself but putting a 3D camera here as one of the, but it's only a billboard of the camera. And you see one mirror in front of you, one mirror, I think, behind. There is also a mirror sphere over here, and as it's impossible, of course, from one frame to understand what's going on. So once I'm just moving the camera and the look at part. And you see that the sphere, you see it both from the back and from the actually there is no mirror here in the back. I take it off. But this is a sphere mirror. So you see the effect and you see the specular shininess over here. See how the camera that we are moving, as a billboard, its reflection in this spherical mirror, and so on. But depending if you're grad or undergrad, you definitely have to implement the specular reflection. You see that the sphere, some parts are more illuminated than the other because of diffuse, depending where the sun is. That might be a hint. One of the parameters in homework 3 is the maximum depth. But why do I need which? So what do I do when a ray? Here is my image plane. I generated from the eye ray that goes through the pixel, and it hits a sphere. What should I do? Let's say that it's not mirror sphere. It's just it's opaque. So you just get that it's blue. So it's only the ambient colors that are getting from this field. What do I do with this way? Homework 3, homework is just homework 2, but you need to use the ambient light plus diffuse plus specular, which implies that once I realize that the ray hits this sphere, and maybe I also validated that the first object that this ray hits, because there might be other objects down the line from this way, but that's the first object that the ray hits. What should I do next? Help.
Is this with or without shading? Is this just like initially?
Homework 3 is absolutely with shading.
No, this example specifically.
With shading.
Okay, with shading.
So you need to get like the normal to where it hits, right? Yeah.
I should have the normal, so I can have the diffuse reflection. That's just the cosine. What about this? I mean, it's a blue sphere, so the whitish spot is not from the diffuse, it's from the specular.
You know where the sun is?
I know where the sun, it's in the JSON.
So you have to shoot a ray towards the sun and see if anything's blocked.
I need to shoot a ray towards the sun to see if it sees the sun. And how do I know if it sees the sun? People, what are we doing? For each ray, I'll generate this ray, and all this part is recursive. It takes the ray as a parameter over here. It's not the only input, but you're doing it per ray. You find out that the ray is shoot and hit your object at P, and from P I shoot away from toward the sun to see if I see the sun. So I just called to see what is the first object this way shoot. So I put a new ray that emerges from this point. That's but I don't need to shoot a ray to every direction. I don't need the set of all the pixels. I just need one particular ray that emerges from this point. toward the sun. And that's how I generate the specular effect. Right? And if this is the spherical mirror over here, then I'll shoot a different ray with same angles, alpha equals alpha, depending on the angle that it comes. I generate a new ray. We don't need to actually compute alpha, you have the formula that gives you this new ray given the input and given the normal. And now what is the color that I assign to this pixel? It's a perfect sphere, perfect mirror sphere, so it's the color of the first object that this way hits. And if I happened to hit a mirror once again, let's say that this way R1 hit a mirror as it continues. The first object is a mirror once again. Then, of course, I'll compute the reflected mirror, and I want, out of my recursion, to return the color of the first object that has a color that it's not in the mirror over here. So I need recursion. That's why one of the parameters is the depth. Depth is another parameter. Yeah. Makes sense? Why do I need it? Because so each time that I'm calling myself recursively, that ray tracing recursively, I increase the depth. And the maximum depth is one of the parameters, just because it's very easy to put a mirror ahead of you and behind you, and without the depth, it will continue forever and ever. Questions? Make sense? And by the way, while I said that Python is fine to submit, it's, I mean, even homework 1 and homework 2 that people send me videos, even with low resolution, like you want to start earlier with this homework, even just with homework 3, even just for the running times that Python will take you. So the actual executing time. And should we decide, you know, I'll give it for you to decide, but I want a unanimous decision. Should we make homework 3 hard deadline, so people will not attempt to destroy their vacation with, hey, I still ran into bugs? Like it's due on March 3, and again, I don't care, but I'm afraid that.
I mean, my personal opinions are to be flexible, because even if they have a bug, like, it's on them to fix it.
We are all human. There is nothing that prohibited you from submitting homework 3 and then enjoy your vacation, but it has potential to. Okay, that's the decision of everybody. I'll be flexible. I was with the homework 2, even though. Okay, but it will not be after the vacation. Otherwise, you will need to start preparing for the midterm homework 4, 5, 6. Yeah. Okay. Hidden surface removal. We talked about the Z-buffer. More Z-buffer. We wanted so. Next slide. Yeah. Z-buffer, what did we do? And once again, that's the intuition of the first loop. Over there, for each pixel by itself, I'll shoot a ray, and this ray needs to be orthogonal to the image plane, which will not work for us normally, so we'll need some trickiness here. But the ray is orthogonal to the image plane. I'll assume that everything that I'll draw is in the image plane. The image plane starts at -1 to 1, meaning that all bodies should be quite condensed and other things just not seen. And for each image, I'll imagine that I shoot a ray, and I'm asking what is the first object that I hit with this particular ray but only for this pixel. I don't care about what happened in other pixels. And the way they compute what is the first object is, in homework 2.3, you are computing the time as the time that it progressed. Here I'll assume that once I have a triangle, I can, using barycentric interpolation, to compute the depth of every point, given the vertices, how far away it is. I'm talking too much. Here is a 2D triangle, namely a segment. Here is a ray, given V1 and V2, and finding the intersection point, which is very easy because I don't change a x and y, just a z or this way. That is changing, hence z buffer. And giving V1 and V2, what is the z value that I'm getting as a linear interpolation of V1 and V2? In triangle, it would be linear interpolation of V2 and V3 and V1, V2, V3. That gives me the depth. And if this depth that I'm getting from this triangle is smaller than the minimum depth that I've obtained so far, meaning this object is closer to me, then, of course, update your nearest object. If you had a few triangles, then the depth value is a depth value, distance to the nearest, the closest to the eye of them. That's a put of x, y, and z that you just calculated. And that's important only if z is indeed smaller than the closest object. Objects are completely opaque here. Change the color of the z buffer. And do it for each and every pixel, and that's it. And one of the big advantages, the order doesn't matter. Do it for every pixel. If you have a lot of processors, namely GPU, do it in parallel for all the processors. So it could take a constant time per a triangle if all the processors work in one parallel step for all the processors. If you have one processor per each pixel, just feed one more triangle and process it. Okay, we went through these slides that essentially you see the depth buffer as a color, and accordingly you are deciding for each pixel, I change the color of the pixel or not. When change a pixel or not, depending on what the depth buffer that I can visualize shows me. Maybe I'll add in homework 4, you'll do, by the way, homework 4, I'm not sure that that's all that it includes. I didn't think about it, but parts that will be included in homework 4 are something that includes homework 2 and 3, or at least homework 2, which are the billboards, except that now the buffers will be allowed. And the big other word that is allowed is texture. You can just put an image on every billboard, and we'll talk more about texture today. That would make the code very, very easy and very fast. Okay, and hence that's how the Z buffer algorithm works. Talked about the barycentric coordinate. We talked about the rastering process that I can compute this interpolation. If I have a lot of processors, then I still need to compute the areas specifically. If I have some amount of parallelization, I can interpolate along one of the edge of the triangle, interpolate along the other edge of the triangle, and now each interior point P, I can compute its value by knowing what is the value in the pixel, say, to its left, and just add a constant. And this constant is the same constant for all pixels in the same row. So it's just addition operation. For each row, no need to divide by area and so on. So that's a pixelized algorithms. And yeah. So data structures for the Z buffer, just two arrays. One array for the depth values and one array for the color itself. So three arrays are RGB to be precise. You might add a polygon, and that's fine. The buffer is perfectly happy. If you're adding a polygon, just make one more pass. If you're removing a polygon, you might run into troubles. By itself, the Z buffer without any addition doesn't have any idea to what was the second nearest triangle to you. Okay. Objects do the geometric processing of the all the translation, rotation, scaling, and so on, and more operations that will do more matrices and projections that we'll discuss shortly. But that's all done only for the vertices of each object, including, by the way, even if you have texture, still, you're just controlling the vertices of the triangle. And now you're doing the rasterizing of each object, do the Z buffer, do it on the image plane, and voila, that's all it takes. Right. So all the geometry is only in the processes level, and once you get it to the processes, then the little mechanism behind the scene do the interpolation of every triangle based on its pixels. Okay, what should I do if I have object with certain transparency? We'll talk more about how to blend colors, definitely coming up, green screen, blue screen, what are the objects that matters, but in general you'll say, I really want to know what is the object that is closest to you, because even with a certain amount of transparency, like if the object is completely transparent in the pixel level, right? If I go back to the Z buffer algorithm, you're running into a pixel that has alpha equals 0, completely transparent, just ignore it. Doesn't affect the depth, doesn't affect the color. What happens if I have objects that are semi-transparent? Still, you care very much about the object that is the closest to you, and possibly the few that are just behind it. So store not the nearest neighbor to you, but the 3-5 nearest neighbors, depending on how much memory you want to add. So that's the A buffer or transparency buffer related to stencil buffer. There are variants, same thing, that stores a few, not only the nearest, but the k nearest. And remember, if you want to store the 3 nearest dynamically, then you're just having the 3 nearest seen so far, one more triangle that comes, is this smaller of the furthest away of the 3, update the furthest away, is also closest, the second nearest, third nearest, and so on. But makes sense. So you just stored there is a picture coming up, a buffer, stencil buffer for every pixel among all the triangles that you have seen so far for the object. This pixel by itself doesn't care about everything else, stores the color and the depth, but not only the nearest to you, but the few nearest to you. There, maybe second, maybe third, with variants about it. Maybe you want to take the depth into the transparency of each pixel into account, maybe not, but then at the pixel level, you are doing the color blending of the few objects that are closest to you and just ignore what is the rest. Lights doesn't penetrate through more than a few. Okay. Yeah, and I will not distinguish between the A buffer and the Z buffer. And let's switch into viewing. And back into transformation. I'll remind you, remember we want to, the JSON file tells you here is a camera, here is the up vector. The same goes also if you have the Z buffer. You have the camera parameters, how do I use the Z buffer for all of them? And just to remind you, if I have 1 point in the XY, where is the slides? Where are they? Yeah. I have two coordinate system. Let's say I represented the point P, I represent it in the, I want to say, I prefer to have the camera at the global 0, 0, 0, because my graphics hardware is built for it. That's where I want the camera to be. That's where I told you that the camera is, that the I is, that the E for I. And I also told you what is the up vector and the lookup, and you generated UVW. As before, I'm repeating stuff that we discussed already. And here is UV, for example. And now I can represent P, one of the obstacle, one of the vertices of the triangle, as go to the I, and go some direction. Constant times U vector, U up, and another constant in the V direction. Maybe from the I to get to P, go in the U direction by half, and another minus 0.7 in the V direction. And that's one way to get to P. And the other coordinate system is I, where I want to represent the same point P, but I watch it from the point O, or maybe A. And here, again, it doesn't matter. It matters, but it's completely symmetric if you want to move the camera or you want to move the world, just depending on the direction of the matrix. I can also get to P as go to O, 0, 0, plus some go a bit in the X direction, go a bit in the Y direction. How do I switch between these two coordinate system? Well, we mentioned this matrix every time. I mean, homogeneous coordinates, if I have one, if I have the identity matrix, I have the identity matrix with 1, 1, 1, and 0 elsewhere. And next to it, I have a, X, E, Y, E, Z, E, the coordinate of the I, and 1 at the end. This matrix makes a translation. Takes 0, 0, I have it. How did I put it on the slide? Take O and move it into E. Right? So that's one part of the transformation. That is take up and down, and take the representation of P. Remember, P can be represented as go to E, the I, some direction to U, some direction to V. So to move it to the I, before or after doesn't matter. Move O to E. And what about the rotation? That's where the little magic happens. That all you need to know about the rotation is low. You don't care about cosine of everything. You don't need to. You could, but if I want to represent the rotation as 3 parameters, if I want to represent the rotation from in general coordinate system, and I can know what's called the Euler coordinates, that is, would rotate with respect to the x-axis, then rotate with respect to the y. And you can be done with this, and probably you will need to know it if you want to animate rotation, except of the case that it doesn't work, which brings us to Gimbel's work, which will bring us to the next, one of the next topics. But anyhow, you do want to think about rotation as concatenation of rotation about one of the axes. For our purposes, it's not needed, and it's actually very wasteful. Much easier to just we know what is a vector U, we know what is a vector V, and knowing it, we know what is its representation in the XY coordinate. So as a rotation matrix, all we need is to take the vector U and represent it in the XY coordinates, which we do, write it as a column vector. The same goes for V. Next slides will also have a third vector, W, and write them. And now all you need to do is just multiply the translation matrix by the rotation matrix, and all, by the way, you can combine it into one matrix. You don't need to. You can apply the multiplication, but especially for debugging, it's convenient to remember what you have in the rightmost column is always the translation. As long as this is 1, rightmost is a translation, and the other things are normally the rotation. So that's how you write it schematically, and it's quite obvious if I ask you, like, geometrically, what is the inverse of this matrix? Yeah, it's kind of, you can geometrically realize that inverse of two matrices, you have this question in theory part of homework 1. If you're rotating by 30 degrees, then the inverse should be, when you word it out, inverse should be two matrices that if I apply both of them one on the other, it takes a point and leave it exactly where it was originally. So if I rotate it by 30 degrees, minus would be rotated by minus 30. Like I had a few, skipping the homework, I had it, I don't remember if I asked you. In the homework, I had cosine 30, sine of 30, minus 30, sine of 30, cosine of 30, all of it in the power of 20. What is, please calculate this the result of this matrix in the meter. Right? And it's either very scary if you don't realize that it's rotation, or realize that it's rotation by 30 degrees that you apply 20 times. So 30 times 20 modulo 360, whatever the result is. That's what you're getting. So it makes sense. So once you realize the geometry behind it is completely trivial. Okay. Orthographic, mentioned. Perspective, mentioned. Perspective plus hidden surfaces, putting it again. So we have the object space, and how do I tell my graphic pipeline about the object parts? It's also a bit tricky. Sometimes it prefers to assume that the location of the object is fixed, and if I want different copies, I'll just move the plane each time to replace the plane to where it was. I want to move into the camera space. I gave you in the JSON I and up and look at. And now I need the projection transformation that will move to orthographic projection. And actually, orthographic projection will not be enough. I'll have for orthographic wrapping. It has a few different names, but just orthographic projection, that we'll discuss next, will not be sufficient, but will be a good start. And then I want to represent the new shape after all the transformations that are over here. So I can use just the z values, because then I can use the z buffer. Z buffer doesn't want any other transformation. It wants, when it shoots a ray, it wants to assume that this ray is parallel to the z buffer. And it will also be convenient that the image plane, that's a bit traditionally came, that the image plane is -1 to 1, 1. And that will require some work. How do I make perspective into orthographic? So, not discussed. This one, viewing transformation, if I want everything to be in the canonical plane, all the objects that I'm going to show. Pieces that are not in the object space, in the canonical space, just don't get to be seen. And it will be nice to assume that it's over here and it's all float. What are the pixel space? It needs to be, I need to know how many how many rows I have and why. I need to, how many, yes, and why, how many rows, how many columns. And you know, the first pixel is half, but the largest pixel should be maximum number of pixels -1, maximum number of rows -1. Makes sense, right? So it's all stuff that you already handled in homework 1, actually. Just show it how it's done in a more traditional way. I have one rectangle that I'm not going to rotate. I just want to translate and scale so that now the lower left corner will move, the x left, y left will move to the corner of a different rectangle. XL prime, YL prime. And the X high, Y high, so sorry, L is for low left. X high, Y high, that's where the original X high, Y high started. That's where the upper right corner should be mapped to. So let's see schematically how to do it. I'm sure that all of you can do it with various other ways that you developed for homework 3. But based on elementary transformation, you know, once again, the joke, mathematician, coffee pot, let's start by translation that will move the lower left corner to 0, 0, which would move the high upper right corner into, what is this, x high minus, I moved it by x low, so x high minus x low, y high minus y low, that's where the upper right corner, lower left corner at 0, 0. Now, I want to scale it, so that would be its length. So I want to scale it, so after this transformation, from x high, I'll move to x high prime, but minus x low prime. Well, why do I need this x low prime? Because now I'm going to translate it in the opposite direction, putting the lower left corner where it should be, and then the upper right corner will be just translated. So translation, scale possibly by different x and y. I agree that that's only z. Interesting, followed by another translation. Translate by minus xl minus yl, making the lower left at the origin. What are the scale here? That's where we want to, it's nice to think that it's always minus 1, 1, or that it's 0 to 1. What will be the scaling parameter? Well, it's completely separately for the x, completely separate by the y. If I want to enlarge it by 2, then the height, or then the width of the new rectangle, should be twice the width of the old rectangle. Here is the width of the old rectangle, x high minus x low. Width of the old rectangle, here in the numerator, is the width of the new rectangle. That's a scaling factor by the x. And similarly, the height, scaling factor in the y. Translate, scale, translate. So that would be the last step. The step before that would be the scaling, and that would be the first translation. Now, taking the lower left corner, putting it at 0, 0. Once again, any matrix that you have now in three coordinates, that is homogeneous coordinates, it's 4 by 4. Anything that you'll write and then the right column stays as number 1 implies that it's translation by these 3 numbers. And when you multiply these 3 two, you're getting that the upper right is a translation by itself. You don't care about what happened in the rest of the matrix, translation for rotation, and so on. Okay. So I want to generate eventually a projection, and I'd like it to be into the canonical volume. Lower left corner, -1, -1, -1. Upper right, 1, 1, 1, and it's all orthogonal. Okay. Now, there will be the fourth term that we'll talk about, or that you're always generating. So far in the ray tracing, I didn't care what is a minimum distance and what is a maximum distance. What are the advantages to also tell you what is a minimum distance? How do I tell you about this first one? In particular, I can tell you what is the opening angle, which you do have, you do need it. and I need to tell you what is the direction of the lookout. And the up vector just help you orient it. So this edge, the first one, is parallel, is axis orthogonal to you. So assuming that it's already orthogonal. What are the advantages of telling you what is where is this storm instead of being infinite? Why is it, what is the nearest part and what is the furthest? Is that there are a few. For ray tracing, you can just decide that there is a maximum T, and behind it you just don't try to show because maybe it's too small and it's already subpixel, or you're using other type like environmental mapping. Remember what's environmental mapping? You are using as texture the walls of the world, putting 6 world. Very useful if you have outside simulation of your outside in the nature. So it's nice that you have, for efficiency, it's kind of important, a bit for the ray tracing, but that would be less crucial for us. For the wrapping projection transformation that we'll show in a bit, it's really crucial that I have the smallest and largest. And this would be the force tool. I can use clipping, or the full name would be force tool clipping. Objects that are outside of the force tool I don't need to worry about at all. Just like backface queuing, just efficiency. Outside of the force tool, check it first, and I'll show you how to easily check if an object is inside the force tool or not. Hint, it's not convenient to do in this type of force tool, but after the perspective projection, when everything is parallel to the X and Y and Z, I just ask, hey, is the X and Y and Z actually make it to be in the, now the force tool just becomes a rectangle or a box. So it's helpful for clipping, and it's completely necessary to move from orthographic, from perspective projection into orthographic. Okay, and how to tell you the force tool? I can specify the up direction and the direction of the look at and angle. Alternatively, I can tell you up and look at, and then tell you about two corners, for example, lower right, bottom up, left, and so on. So I'll tell you about two colors. And what I really want to remember out of it is what is a near and far. What are these gaps? That refers to the Z parameter. F for far and for N for near. You'll see it's really important. Okay, and this slide in a painful way explain to you what I want to do after as a canonical bottom that from this point things are. This is the moment that you decided that it's all in inside, that you converted from a perspective into orthographic projection, even if it's not in the canonical volume, but now you have everything lives inside an axis parallel box. You already translated the word, so the matrix is where the Z buffer of the graphics rolls into B, 0, 0, 0. You already rotated everything, so the direction is parallel to the XYZ. You now just need to scale things. And you can assume that to start with, it's the lower bottom near and the right top far away. And as we said, scaling to put it in the -1 to 1, that's true. Okay. And near is smaller, in its up. Near is closer to you than far, but remember, you're looking in the -Z direction. We discussed it. That's because to keep it as a right-hand coordinate system. Why do I need to keep it as a right-hand coordinate system? Because otherwise no rotation will do the trick for you. It can work for 2 of the axes, but not for all 3. Rotation, we already discussed. How do I generate rotation matrix? Just write the 3 vectors, UVW, in the XYZ, which are essentially just take the, once you generated them, you already get them in the UVW coordinate system. Usually, and don't go backward, there, and UVW, and translate by the I, that's this matrix without the -3 here over here, take a point from the XYZ coordinate system into the UVW coordinate system. With a minus with a -1, it's just the opposite direction. And as before, you don't really need to translate to know what is the inverse matrix. You could, but you don't need to ever compute the inverse matrix. Okay, let's talk about how do I get the perspective from orthographic projection to orthographic projection. So I have a bunch of points, x, y, z, and I want to convert each one of them into x, y, maybe not the same. If I want to just do orthographic projection, just ignore the x and y, but it probably doesn't take any perspective into account. So you will have to use this matrix of take x, y, z and just multiply it as x and y, but it will not work for the x and y. It's very unlikely to work if x and y are the very original set of points. They need to go through a bunch of operations before you can just ignore the z direction. Finally, something that I'm excited about. So, some new ideas. Here is the image plane. I'm using orthographic projection. I told you that the image plane, which I'll assume right now, the image plane goes all the way from minus infinity to infinity. But I'll tell you that the image plane is at distance d. Here is a point P1. Its coordinates are x1, y1, z1. Remember, z is z, x, y toward you. If that's x, y, z, and what pixels should be rendered red if this original vertex is red when you are projecting it using orthogonal using perspective projection, what pixel, one of the pixels should be rendered red? What way should I shoot to hit this pixel? Well, it's very easy to calculate. Look at this triangle. Let's look at the x divided by the z of this vertex. It's a vertex of a triangle. You just don't see the rest of the vertices. Again, look at the x, the height, divided by the z. Let's look at the pixel that was just rendered red because of the ray tracing. I know what is the distance of the image plane, which includes the location of all these pixels. I know the distance from the eye to the image plane. That's d. It's part of the input. What I want to know is what is x1 prime. The projection of P1 onto the image plane if I use orthographic projection. If I use perspective projection. All I stand and these are all the ways that I'm shooting. Triangle similarity, remember? Elementary school, maybe mid. This divided by this should be equal to this divided by z. That is, x1 divided by z1, which are part of the input, should be equal to x1 prime, which is the unknown, divided by d, this part, or x1 prime, what I want to find, equals to d times x1 divided by z1, right? The larger z is, the furthest away the object is from your eye, the smaller should be x, and the same goes for the y that you don't see. That's great, it's very simple transformation, but it's not a linear transformation, meaning that I cannot apply it via matrix multiplication unless I'm using homogeneous coordinates. When I told you about homogeneous coordinates originally, I mentioned a few applications. One of them was translation. Obviously, I couldn't do translation without homogeneous. Here is another one. Let's ask what is this matrix? 1, 1, 1. 1 over d is doing for us. Remember, d, the distance to the image plane, is part of the input. It's different for each point, but here is a coordinate of the points in homogeneous, and usually the input we are just giving x, y, z, and 1 at the end. We don't care about it. What happens when I multiply it by this matrix? It will be x1 times 1, y1 times 1, z1 times 1. So far I did absolutely nothing. And the last parameter is this column, this row, 0, 0, 1 over d, 0, times x, y, z, 1, giving me z over d as the first parameter. And now it's homogeneous coordinates, how we understand it. Take the x divided by the last, take the y divided by the last, take the z divided by the last. So it's x1 divided by z1 over d, y1 by y1, z1 divided by z1 over d, and 1 stays 1. Look at this guy, z1 divided by z1. What do I, and here I have 1 over d, which is d. Exactly what I wanted. Get to the image plane. So the three as a point, that's where this point landed. So now I can use it. And if I have just one billboard, I can project it immediately on the image plane, and I don't need anything else. So that's a good start. By the way, I can write this matrix also. I can take the very same matrix and multiply all of it by a constant. Would not matter, and I'll write it in a different form, which will make it more similar to what is to come. I'll multiply this whole matrix by d. So I'll have d. This is the first one, d, 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 that stays 0, that becomes 1. Okay, so that will be a bit more similar to what is to come. And that's fine. For a projection from a 3D object into the image plane, it will work. You can take one billboard and just project each pixel directly. You don't need a ray shooting instance. What I have absolutely no idea from here is I'm going through, I want to use the Z buffer. And the Z buffer can say, hey, I have 2 points, P1 and P1 prime, that both are mapped into P1. I have P1 and P2 along this way, and both are mapped into P1 prime. And once I used this transformation, they both have exactly the same D value, the same Z value, which is D. And I have no idea which one is closer to the viewer. So this projection did half of what I destroyed, but I lost the depth. And there is no way that I can save the depth, by the way. If I want this projection, it will destroy the depth. So the depth will not, I cannot maintain it. Here is a perspective wrapping. Remember, I have the near, I told you that you need the near and I need the far. And this matrix, which is kind of similar, just replaced D with N. It will have the N. Here something strange happens along this row. What happens to the D? And the one over here is the same one that you see in this matrix. Remember, so this will be the perspective wrap, which looks extremely mysterious to me and keeps me very frustrated for a while. So then I don't understand, what's coming next. So just to make sure that the matrix that I applied for each and every pixel that I decided that I need to render, it already passed all the clipping processes, and I want to map it into some location in 3D. And if I'll map it into some location in 3D and ignore the Z value completely, it will just be orthographic projection. I'll say it again. I want to apply it for a vertex XYZ, and it will not be on the image plane directly, but had I both project it using this matrix and then ignore the Z value, then it will be already in the correct pixel. That's just the orthographic projection. Okay, so it's fancy words. We're using hyperbolic equations. What's going on? So you know what I'm doing when I don't understand. So I specified the angle, but doesn't matter. The I is at 0, 0, 0, because as I said, that's what our hardware likes. I told you what is the distance to the near. Can use the near part of the forced room. The forced room, by the way, that's the look at. That's just the what used to be the x, and now we think about it as a z value. Z is always the depth. This will be the x, y goes toward you in this image. And I told you what is the distance to the near plane, which right now I think about it also as the image plane, the same part over here. And I also need to tell you what is the distance to the furthest away part. And I took a point A over here, one of my points. Look at the way that goes from the I toward A. That's where A should land in the image plane. If I project A into the image plane, that's where it lands, exactly where the ray is doing. And what I did is just to apply the matrix that I saw before, just for these values of near and far. And I can change, of course, near and far and things will change. So A lands in this particular point. A2, by the way, is also on this way, also lands in this particular, at the very same point. Right, it is, that is both A and A2 lands on this pixel. Okay, and if I move if I move A2 a bit, then of course this pixel are changing. This way from the I to both A2 and A will be changing, and had I ignore after the transformation, if I ignore the Z value, that's where they landed. That is on the very same pixel on the image plane. So why couldn't I just do with this matrix? Well, I said that the depth is destroyed, and it's kind of true, but there is one very cool property that is maintained. So here is A, and A prime, which is the transformation applied on A. Here you see A prime. That is, if I'll take A prime and just project, ignore the Z value, just project it on the image plane, it lands in this correct point. The same goes for A2. But for a viewer that stands right here, what should be the color of this pixel, given that this vertex is red and this vertex is blue? The one that is closer to 0, so this vertex needs to be blue. Whereas, what happened to A prime? It got some Z value, which is related to its original Z, but it's definitely not the same Z value. It's not the same depth. It's not the same distance from the viewer. The same goes for A2 over here. It also mapped to some points, but, and here is the beauty of it, as long as A2 is closer to the viewer than A, then the projection of A2, or the Z value of A2, is smaller than the Z value of A. Make sense? So after the projection, the Z is different, the depth is different, but the Z buffer doesn't care about the exact depth. It just asks who is closer to me than whom. That is, at this location, at this point, the pixel, the projection should be red because A is red. At this point, the projection should be blue because now A is closer than A2, which is exactly, that is, the order maintained. It's a great midterm question. The order maintained, the exact location have a strange location to the original Z. But if two vertices of triangles appeared in different order along this way, after the projection, the one that is closer stays the one that is closer. The exact location different, the relative order is not. But why did I need to tell you what is a near and far? Well, once I moved A to further away, beyond the near, I make A outside the forestrom, either here or, if I can, also here, and the same goes for A2. No guarantees about what's going on when you're outside the forestrom. Definitely when you're closer to the eye, you're outside the forestrom, but still in a place that the camera sees should be represented. But now the Z is somewhere way, way behind the camera projection to a place that your standard way shooting will completely ignore. Okay, so now you should all, if I give you a set of triangles in 3D and ask you how to place all of them in the way that the Z buffer likes to work, -1 to 1 will be the image plane. Given the near and far that I originally gave you in the input, now I do need to give you, I don't think that I have it in homework 3, but next one maybe. You'll know to place all the objects inside this forestrom, clip everything that is not in the forestrom. That you, if the input is like in the image plane, you don't have the near and far. If the input is like in homework 2 and 3, you don't have the near and far, because you don't need it for the Z buffer, but you do have the opening angle, which is equivalent, because now you can specify where are these corners, and that's just the cone is infinite. So you're ready to use the Z buffer, and I wanted to give you now a few minutes introduction to what's coming up. We start to talk about texture, our next topic, and of course, unless there are any questions so far. So texture to start with is just billboard, except that you put a billboard on it. Usually it will be a triangle, depending on which packages exactly you're using. Sometimes quads are acceptable. Sometimes you'll just think about it as all I need to do to use the hardware supported Z buffer, and we'll talk more on Wednesday about the math, but all I need to say that the upper left corner is relevant to one particular point in an image file. The same goes for this corner, the same goes for this corner, and the exact pixel in the inside the image is interpolated by hardware based on the, guess what, barycentric coordinates. Once again, it will give you the XYZ. You'll just do it separately for each one of the two triangles, and it doesn't care that it's actually in the same billboard or not. what I want to give you a heads up is what other things we can do with texture. It's extremely strong concept with many more applications than just just to put images, of course. Okay. Other parameters beside putting billboards that we already used as really imposers and multiple imposers at the same time. But the same goes for make wood looks like wood, make the carpet looks like carpet. That's like the no-brain thinking about. And of course, if I tell you that actually the image is too small and I need to tell you what's going on here, then the coordinates will be wrapped. Because maybe to represent this carpet, it's enough to just give you a small part of the carpet and now just redo it. So it will go to 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and so on. Just do it all modulo. Let's see the less trivial applications. So we discussed how do I solve the mirror problem. That I want to show you an image with a mirror. It's not a mirror in a mirror. It will be harder, just a single mirror. How do I do it? I put the camera in a different location and see what this camera sees. I can also ask in the image what does the light sees, and now overlay it, especially if I have shaders programming, which we do have, like WebGL, OpenGL. I can overlay it, and we'll go more in the light, with what the camera sees and specify each pixel as illuminated only if it is seen by the camera. And the math is not nearly as scary as it is. Or, I can still overlay it, but I can specify that the texture file that I'll give you is, here is my original image. It consists of very few polygons, one sphere, one cylinder, very few faces. Here is an image that I gave you, and I maybe gave it to you as zeros and ones. Overlay the two, and voila, each pixel by itself. How do I know what happens in this particular point? I'll use the mechanism of the texture separately for each object by wrapping up this image, this texture, along the cylinder or along the hexagon, along the prism. And at the end, what do? I just make it the alpha transparency of each pixel separately. So at this point, I just used the wrapping, the geometry that comes from the mapping itself, from the texture itself, but I don't understand it as a texture. I understand it as a transparency that either I can see through the pixel, see whatever the image at the end, the sky out there, or this pixel is metallic. Okay, we'll talk more about the math behind it. I can similarly create the specular effect instead of running the whole gamut of the specular effect. I can specify it more. What about, can you tell me other application of texture that you might remember? No, before I continue.
Billboards?
Yeah, billboard imposers, definitely. Yeah, it's not a question about this course. It's just what do you know about from other graphics games, blenders that you played with. It's something that comes with lots of names. It's similar maps / displacement map. I can say I know that my image hits a surface and the surface has normals, but now I'm going to alternate each normal separately by some amount, and this amount is given by a matrix, and this matrix is given as a texture. That will give me different normals, or different shapes for each individual point, and I can create the impression of a very rough surface very easily by just playing with normals without really affecting the ray tracing or the hidden surface part. Just each pixel where in the part that I know that is already seen. Yeah, we are just.
It's kind of like the image of the moon where it was more lit up than it should be versus the completely smooth sphere because of the
Absolutely, great example. I can take the moon applied a texture only to just tell me how on the perfect sphere the normal are changing, and that will be. I didn't think about it, but it's excellent. But that would be exactly resolve it. Thank you. See you Wednesday. Bye-bye.
Quick question about. Yeah, I can
I'm,
wait.
I'm happy giving.
No problem.
That was don't know how to fix more arbitrary.
So you give the example of translation where you take the closest vertex of like the rectangle and you move it to the origin, and then you proportionally move every point to that point, and then you move it to the space you want it to be. Couldn't you also just shear the object in the higher dimension by some delta of where you want to go, if you know where you want to go, and then apply that matrix? So.
Yeah. It will not change the angles? So saying that it's shearing. If I'm staying in 2D, with or without homogeneous, I'm in trouble. If I'm staying in 2D, definitely not. Shear will take a rectangle and move it to be a trapezoid.
What about a shear if you store the 2D points in a matrix, but you make the matrix a 3-dimensional matrix?
If I use the homogeneous coordinates, I don't. Cute question. I don't know.
Because if it's 2 dimensions, you don't care about the angles of the 3rd dimension, right? As long as you.
I agree, and I don't know in particular. You want to take if it's axis, if it's symmetric in x and y. I'm a bit scared because there is plenty of other points that needs to. Let me think about it.
Yeah.
It's cute. So can I express resizing as a shearing in higher dimension? It's not in higher dimension. It's if your hope is that it's shearing in 2 dimension but with homogeneous coordinates. That's the only hope.
Okay.
I think that when I'm playing with the last dimension, I'm doing the scaling, but I cannot scale the original image. I cannot express the scaling without the translation. So I'm.
What effect would this matrix have on? So, say you want to move this point by these deltas, but it's in 3 dimensions, but I'm storing it as a 4-dimensional. That's just a translation, right?
Correct.
So if I have some object that is expressed as a vertex, which is just a list of points, if I want to move them all, do a translation of the whole object to keep everything parallel to the faces, I can just apply this matrix to whatever the delta is, right? Because if I have,
Yeah, that's
okay.
all I do. But when
There's no
doing the
rotation
ratio,
involved, right?
yeah, but at the end of the day, it's just one matrix that works for the whole world.
Yeah.
And I rotate all the rotation and the perspective wrap and this whole construction. And once I have this matrix, I push it for every time that I shoot a ray, for example, then it's without the perspective ray. But translation rotation, every time that I shoot a ray, either I see the world through this matrix that is the coordinates of the rays,
Yeah.
the coordinates of apply it all to the ray, or apply it on the plane that it's of the billboard. I interrupted your question, I think.
No, I mean, this would be just applied to the translation of the object in the same coordinate space. Because I mean, if you want to translate the whole world, you apply this matrix to everything, all the points of all the objects. But I think a better way would just be to change the origin.
Well, but algorithmically, I'm saying the sentence I applied it to every object. The sentence is misleading because it does not suggest an algorithm that starts by let's take every vertex and apply the matrix to it. That's,
Yeah. Right.
every object, when it needs to render, the vertices are not where they are in the input file. Vertices are in the matrix times these vertices when I applied it. Or I take the viewer and change the viewer, the direction. Yeah.
You're applying, yeah, there's a matrix in between the viewpoint and then the world you're trying to see. So
There is a single matrix, yes, the
Okay.
connector. To generate this matrix, I need to do it as a multi-iterative process, but at the end of the day, it's one view matrix, every pixel instead of, when I should ask what is a Z buffer, it's a Z buffer of the applied triangle, but other triangles I don't worry about.
Okay.
Yeah. Yeah.
No, that's a sufficient answer. Yeah, thank you.
I suggested maybe I try to think about it as it's taking the ray and teleport it every time that I generate a ray. But yeah, it takes a ray and teleport it in other location, but this matrix is relevant only when I need to ask, is this ray hit this triangle?
Yeah. Okay, thank you very much. Have a nice night.
Sure. Hey.
It's just real quick, I want to let you know. So I should definitely have homework to by tonight. Well,
Okay.
I'm going to do my very best. The only thing I have left to solve, I've solved ray tracing, the spheres, billboards, transparency, all of that. The only thing that's strange is my FOV feels inverted, where what will happen...
3 seconds.
Oh yeah, of course. You can, so I
I have a 15-year-old that needs to.
If you need to leave, that's totally fine.
I probably have to leave in 10 minutes or so, but I just want to coordinate. So,
So it feels like my FOV is inverted between, because if you have 60 FOV, then you should be seeing a larger rendition of the image. If you have 120, you should be seeing a smaller rendition because the FOV is larger, so it's looking at more space. But for me, I kind of have the opposite.
I'll make a guess. I gave two methods to generate the distance. That is, one was assume that the distance between the pixel is 1, and then is 1 between a pixel and the next pixel, and then the image plane is far, far away from me. The more pixels, the further away. Or I'll assume that the pixels are very dense, so the size of the image plane is always the same, and then that's kind of the standard way, but I found it less natural. That Z, that would be alpha half. The length of this one is 2, that is -1, and there is plenty of pixels always float coordinates. And then it's 1 over tangents, if I remember right, alpha half.
Yeah.
If you combine between the two, then it sounds like what you are describing. But
I can show off. Let's see.
do you want to?
Yeah, we can. Sorry, for some reason my touchpad has decided to
If you
disable
want
for
to-
a minute.
There's another option.
I did, so I've decided also to swap to Python just because I couldn't solve the asynchronous problem with JavaScript where it would refuse to run the JSON parser before it ran my rendering loop and would fail repeatedly.
Don't go away.
You-
Yeah, what? No. Hello. What? You want call? 15 minutes, yeah. 6:45, 20 minutes. 15, fine. See you. I got 10 minutes.
Of course. Let me close that. So I swapped to this. The only libraries I'm using is like JSON for just reading the JSON basic library for images.
You're worried much more than I meant students to worry. The same goes for submitting it tonight. Now,
Well, it's because the other reason I switched to Python is the gentleman who did the discussion on NERF. We wanted to work together on homework 3. So I decided to do it in Python because that's his preferred language, and I wanted to familiarize myself with working with graphics in Python.
fine with me. A warning ahead of time. I worked extremely little with Python. I asked yesterday students to send me homework 1. Python implementation that I got was really, really slow.
I believe, isn't it because it doesn't, there's something with Python about it running, like not using like the right, there's something. I know there's a problem with Python. I'm tempted to switch
Homework
to C.
4, where you use the graphics hardware, it's all fine. The implementation of loop, for loop in Python is just extremely slow, and here you have at least 2 nested loops. So
Well, I may swap the implementation to C, just to speed things up.
My
for homework
recommendation would be do it with 50 by 50 pixels and very, very small images, and
Just to
scale it
verify
up
things.
just
Okay.
when everything else is fixed. Otherwise,
So I have
very few pixels.
I have my array hit register, vector class, sphere, billboard class, which the thing we should actually be looking at is camera. So in the camera, I of course get I look at FOV with height. I was reading the book because someone recommended to me that the way to deal with creating the image width and height was using the FOV. So depending on what the FOV is, you can construct the width and height of the image plane and then do everything relative to that.
So if I don't have good answer if it's not the same width and height, then
Well, it's a 1-to-1 ratio. they're the exact same width height in this case.
If they're the same, then yeah, so you can decide that it's always the same size and control this distance, or you can decide that that this is fixed at the number of pixels. Doesn't matter.
Because currently I'm doing like
I
this.
don't know that one method is better than the other. Okay.
So I'm doing the focal length is obviously like FOV over 2, and then that's over half of the image plane width, which, you know, in this case is 1. So it would be 1 over 1 over tangent of alpha over 2, just following this to calculate D, right?
Yes.
And I think it might be something to do with...
But now if you use the other method to generate the pixels, like you need to be consistent. It's either a distance, at this distance, that the total the width is 2 fixed, and then the gap between the pixel is number of pixels divided 2 divided by the number of pixels. Or you are assuming that you're adjusting the distance to the field of view and keeping the distance between the pixels. If you're combining between the two, it sounds like what? The bug.
I was using the textbook's way of defining, because, you know, it's the equation dw plus, like, I called it u, which is probably stupid, but whatever. Where you define u and v based on the top right.
And that's, you forgot
Oh, the I?
Yeah.
Yeah. Wait, so is this, because I was using this equation to calculate the direction of the ray. Is it supposed to include the I?
The way, the way I explained it to myself and explained it to in the class was, I have one mechanism that takes 2 points, let's say I and P, and shoot away from the I to P. That's one mechanism, and completely separately, I'll generate a set of points. It's not vector, it's points that are at the coordinates, exactly what you wrote over here, and now I'm using this mechanism, which is not the most efficient. You could have, but I thought that it's more robust to bugs that I think about it as separate task rather than to think about the ways as vectors and then the I is as you're describing. I don't need to have it. And then the pixel are with respect to the I.
So you would suggest splitting up, so this is the ray direction, this thing, and then what you do is you first calculate all the points relative to that are on the image plane, and then you take each point and you do
a ray that emerges from the ways that it, to be precise, it's I plus T of Pij minus I, all of it, of course, normalized. If I cared about it. I mean, it will work if you don't know. But,
and then, so this equation, is that solving for the ray, like where the rays go?
This is the direction of the ray, but it emerges from the I. Ask where is the ray at T equals 0.
The way I set up my ray class was it had an origin that had a direction, so I gets stored into its origin, and then this gets stored into its direction.
That definitely right. Double check that at T equals 0, the ray is at I.
Okay. That makes sense. Well, thank you. I will do my best to get this to you by tonight.
There are various different ways to solve it, and each one is perfectly fine. But merging between two sounds risky. So
then because I genuinely cannot figure out how to solve the JavaScript concurrency problem to save my life. It's something to do with asynchronous function calling. What language would you recommend to write things in so that you're rendering at a decent speed?
I didn't give any directions at the end. I don't know in Python. That's where you both to find the concurrency actually. Check the path values for. You're more than welcome. It's to use any resources live or if you want to solve the original problem. I don't remember. I'm very curious. I can ask Josh. So that is more hands-on on this aspect, Josh Levine.
What's your language of preference for graphics programming?
See if I need it to run fast. If I want to check an idea, I can even go to MATLAB first to check MATLAB. To check the idea about generating the video from the screens. Just use any screen, any screen capture that you don't need to implement anything. Run the animation and have a video capturing the screen.
Well, but if we're rendering, like I know in homework 3, we're supposed to render like multiple frames of.
What?
And so should we render all of the frames individually and then like create a video out of that, or should we be rendering it real time?
That's how I generated it, and that's how I kind of suggest to